And then the next presenter would be John Odi Cabrera. He is a PhD student of UP Diliman. In fact, Odi is affiliated with the other PCARI project, which is entitled Resilient Cyber Physical Systems. And he's going to talk about his work on designing a menu of contracts for demand response on HVAC systems. And then, to conclude this session, Dr. Nestor Michael Grau, professor from UP EEEI, will talk about transactive energy. It's the technology that will enable these technologies that we are developing. So again, the smart grid, it's several technologies coming together, okay, to have a better grid. So we can have a better grid. So without further ado, I'd like to turn over to Claire. So Claire is joining us via Skype. So at the start, well, we have some technical problems because we cannot show video coming from her side. So we will just show you her presentation. She will hear. You will hear her. Claire.
All right, so let's try this again. It's great to be able to present to you the work that we've been doing as part of our PCARI projects. This is joint work with PhD students Rule and Datong, who are currently at Berkeley working on the project, and Rule has been supported by the PCARI project. And then also a former student, In-Soon Yang, who's now a professor at the University of Southern California. And the work that we did with In-Soon was really instrumental in the writing of this project and in our collaboration. So I'd like to start with that. Next slide, please. Okay, so let's just start with an overarching theme, which is the variability and uncertainty in power systems. So variability and uncertainty increase power system operating costs and compromise the reliability. So we can either think of solutions that are new technologies, such as on the supply side, for example, fast start generators, fast ramp generators, or more storage, or demand side flexibility. But we could also think about new market structures. And some of the research that we've been doing in these demand side management issues deal with both demand side flexibility as well as new market structures. Next slide, please. Okay, so new market structures. Here we've been in this project that we started a few years ago. We've been thinking about the idea that we could manage variability and uncertainty by purchasing or selling surplus power in real-time markets. But real-time prices are volatile and it increases the risk to consumers. So basically the idea is to employ real-time pricing, but try to manage the risk of such a contract. So even if real-time pricing would lower bills, the extreme events could turn people away. Next slide, please. So we designed what we call risk-limiting dynamic contracts. This is a demand-side solution to manage the uncertainty of consumers' solar and wind generation and loads, so the kind of variability that we will see in the future. And so the idea here is to use a control mechanism called direct load control, and this manages risk. But at the same time, we develop dynamic contracts between a utility and its customers, which is based on a stochastic optimal control framework called mean variance constrained risk sensitive control. And we use programming to solve it. And this provides a risk limiting capability. And so far we've developed this method and we applied it on data from the Texas utility in Austin, and we found that it's promising. So the reason I wanted to start with this, it's a paper that I've got the citation down at the bottom that we've just published a couple of months ago with Duncan Calloway and In-Soon Yang, is that we came into the PCARI project when we started more than a year ago with this thought of really trying to focus on the design of contracts and demand-side management. And then as we started the PCARI project, we realized that it was important to start thinking more about, if we're going to do such control mechanisms, how do we first sense and get more information about the network and build models about that network and perform estimation so that we can do the control. Okay, so next slide, please. We should be on a slide which is the main outline slide. So I guess, you know that, hello? Yes. So slide 5, outline. What I've given you in the past few slides is a bit of a motivation of where our research group came from, thinking about the design of these contracts. And I think what we realized is that to be able to implement any of these kind of control mechanisms, we better have a very good way for doing state estimation of the grid. We better have a good way of actually doing, control. So, and then, we went back to revisit to demand response and demand-side management. So my talk is divided into 3 pieces. The first is on distribution grid state estimation, and that's joint work with my PhD student, Rule, and a number of others. The second is fully decentralized policies for optimal power flow, also joint work with my PhD student, Rule. And then the third project is a study that we've been running for the past year and a half, which is a demand response study in California. And I thought I'd end just by talking a little bit about that. It's not really part of the PCARI project. However, it's quite relevant for this session this afternoon. Okay, next slide, please. Okay, so where are we? So we're in a, I think that, just judging from the talks that we're going to hear, we've already heard this morning and that we're going to hear this afternoon, we're moving from a fairly passive power distribution grid in which, and this kind of network schematic illustrates it, we're going from unidirectional flow, a monotonic voltage drop as you move down the links, and fairly predictable load with little variability to, and if we go to the next slide, a highly dynamic network. And so these little icons on the network here are meant to represent the kinds of things we're going to start, and we already are, or we're going to see more of in the future. So storage devices, renewables like solar panels, electric cars, smart thermostats, inverters, etc. So the new standard will have all of these things, and as a result, the kind of variabilities that we've seen so far could only grow if we don't design it properly. So there's intermittency and variability, reverse power flow, energy coming into the grid, many connected devices. And the new issues are many, including rapid voltage fluctuations, increased switching and wear, hard to operate. And so the idea here is to really start thinking carefully in this kind of new standard about how we model and control this network. And that kind of is, I think in this project we went a little bit back to basics to do this before we launched into the demand-side management and demand response program. And I'll talk about that at the end. Okay, next slide, please. Okay, so the first problem that I'm going to talk about is of these 3 problems is how do you perform state estimation with limited sensing? Now, this morning you heard from Sasha von Meier, who's our collaborator and is the co-PI on this project. And she talked about novel methods and new sensors and their application, so micro PMUs and how they're applied in the network. And this is this is kind of our core backbone of the PCARI project in terms of the sensing capabilities. So suppose you have such sensing. You're not going to have that sensing everywhere in the network. And so the state estimation problem is quite interesting. So what do we mean when we say state estimation? So you're measuring, and you can see in the little diagram on the left, you could be measuring certain voltages. So what I've shown in black, the voltage at node 1, 4, 9, and 13 may be where you have your sensors, but what you'd really like to estimate are powers and voltages throughout the network. So the actual state could include those as well as many more of the variables. So a number of people have worked on this problem, and really what we have been proposing, if we go to the next slide, is to hybrid state estimation or distributed state estimation. But we're really thinking about, and I think this really starts a theme that all of us on the PCARI project have been kind of working under, which is a theme of, in a principled way, combining models, so model-based techniques with machine learning, and to do it in a way that you can make guarantees on the kind of predictions that you're coming up with. So again, we're showing some results or some of the previous work on this problem here in hybrid state estimation. And let's go to the next slide, which is slide 10. And this is a slide entitled the Distribution Grid State Estimator, or DGSE. So we really view this as a data pipeline for forecasting and state estimation. And we don't need to go through all the details, but if we look at the left-hand side of the diagram, where we have a block which we call modeling. So these are the kinds of things that we can do ahead of time. We could have a network model. It may be, a rough model, but a network model in which is fed into a modeling block along with a load forecast. So we'll take load data, that may be historical load data, and models, and then use that to compute prior distributions on the state. Okay, so in that left-hand side modeling block, it can all be done offline. From a model and load data, compute a prior distribution on the state that's fed into the right-hand side, which is an estimation block, which is done in real time. So here, what we're doing online is updating in real time with, for example, phasor measurements, the state estimate using whatever machine learning technique you want. We use a linear least squared estimator, and the equations are above, but basically we're kind of grounding the machine learning at the beginning with a model that's based on our knowledge of the network and load data, and then we're updating it in real time using machine learning. This is, of course, if we think about, for example, a Kalman filter, this is really what, in essence, a Kalman filter is doing. It's combining a model with an update based on real-time data. And it's really kind of the algorithms that we use are a bit different, but the idea, or I think the essence of it, is really there. So I think, really what we'd like to do, and let's just move to the next slide, slide 11, and this just puts in words some of the symbology we had. So we're out of the models, and the offline piece, we're getting forecasts of unmeasured voltages and measured voltages, and also some second-order statistics on the state and the measurements. And then from real-time voltage measurements, we're basically computing an update of the state. So the linear least squares, the best update given the information that we have available. Okay, so let's go to the next slide, which is slide 12. And this kind of goes back to what we're doing for forecasting. So there's a picture of a smart meter there. That's really just supposed to represent that we're taking, and we have access to historical data of networks and how they're used to be able to kind of prime the learning to get the right solution. Let's skip to the next slide, which is slide 13. We've tried this out in simulation on some of the IEEE network models that are available online. And I think what's interesting in these two plots, they're both plots of the estimated voltage magnitude, but on the top plot, it assumes that you have a sensor at every 5th bus, whereas at the bottom plot, it's every 15th bus. And so you can see the little black stars are the forecasted X. And so the forecasts are just going off and then they're updated when there's a measurement. But we're really using the updated, information, the state to be able to smooth out those forecasts and get an accurate representation of the state. Next slide, please. And so we've done that with a couple of different examples. This example on slide 14 is one of those IEEE, another IEEE network. And here we have this is an IEEE 37 node test feeder. And so basically it's a nice example. The feeder voltages and power ratings were left unchanged here, as were the line segment configurations. But in order to create a balanced network, so this is a single phase network, but we assume that all line segments were 3-phase. And so we sort of set this example up. And then we ran our data pipeline for forecasting and state estimation with 10,000 Monte Carlo simulations. And let's go to the next slide where you can see, or actually at the bottom of, where am I here? On slide, the bottom of slide 14, you can see the AR-MSE, which is the average root mean square error. So this average root mean square error for one of the runs, and so through this you can see the one of the Monte Carlo runs. But if we go to the next slide, which is the it should show. Yeah, so the, okay, I'm sorry, I didn't include the, a number of, like, the average over all the runs. But basically, we're seeing that, where the forecast may be deviating, the estimation is giving us quite a, a good measure of it. So we think this is a promising technique. And if we go to the next slide, which is slide 15, it kind of talks about what we would like to do with this. So in general, we'd like to take all of the kind of historical data we could, like load data, weather data, network model, to develop forecasts, and then basically use the learning to do state estimation up for voltages. And so we have basically some ideas about doing some hardware in the loop testing up at LBL, which we want to try to do a little bit this summer. And we've also got a project where we're really trying to do a 3-phase network implementation of this. Okay, so and so now we can go ahead to let's skip over to slide 17, which should be the outline again. So I talked about the first piece, kind of really thinking about carefully about state estimation using models and by combining models and data-driven methods in real time. So taking that theme a little bit further, I'd like to go on to the second piece of our work, which is this fully decentralized policy for optimal power flow. Okay, so let's go ahead to slide 18, please. And on slide 18, if we think about now the problem of control, so we have inverters throughout the network. So basically, system operators have traditionally had to deal with switches and transformers and capacitor banks. And historically, control has, the actual control of the network has been based on coarse load forecasts. So, things aren't really changed that much. But now, kind of with our new standard of this grid that we talked about, there's going to be more distributed energy resources, batteries, EVs, solar, and they're going to enter those DERs are going to come in through inverters, and this will be at probably a much faster time scale than historically it was. So the idea is to try to think about how we would redo, in a way, the optimal power flow problem, OPF, optimal power, in this new standard of a grid which has all these devices and inverters in them. Okay, and we'd like to think about possibly, solving this problem in a decentralized way so that we could even do local control at the inverters. So let's go on to the next slide, which is slide 19. And this is kind of an overview slide of what we'd like to do. So you see our, on the upper left-hand corner, the distribution network, which we've shown a few times now. So that's kind of representing what we talked about, so network model and historical data. So we can go ahead and we can solve on that network the optimal power flow problem. So we move over to the upper right-hand corner. And optimal power flow basically takes the constraints, takes the load forecasts, and computes an optimal power flow. And there's a lot of work on this, going from the older nonlinear equations of Baran and Felix Wu to some linearizations and convex formulations of this done by Stephen Lowe at Caltech. And then some people have thought about that, but how do we then, take into account the fact that these networks are changing so quickly? So how do we actually do local control when we've, maybe solved an optimal power flow for an approximation of what the actual network is? And that's really what we're treating in this second problem. So the idea is to use optimal power flow to determine the optimal inverter set points and local data, and then use machine learning to derive and to compute local controllers, which basically learn a mapping from its measurement to what its contribution should be were it to participate in the optimal power flow scheme. So that kind of gives us a bunch of local results which could be aggregated to a global solution to the optimal power flow problem. So that's the idea, and then I've got a few more slides talking about some of the details here. So let's go to slide 20. And I wanted to start with this because this I thought was sort of set the stage. Again, what is our test bed here? We're using a real distribution feeder. This is one that we got from a database. It's a feeder in Arizona. And it's substantial, 129 nodes, 53 loads, 28 inverters. We're assuming balanced power flow, and it's a single load profile. So that's the network model. But then we took a database of load data. This is an available database called Pecan Street. And we populated Arizona node with historic load data. So this is, real residential consumption and generation data, and it's, provided every 15-minute interval. Okay, let's go on to the next slide, which is slide 21. So we solved the optimal power flow problem on that network. So that's, a standard problem that's been done before, and that determines each inverter's output, which we then go to slide 22, we perform machine learning. We basically do regression, which does this mapping, which, each inverter, each distributed energy resource learns a mapping from its own measurements to what its contribution would be were it to participate in the optimal power flow scheme. And so the global solution that we do first is just kind of a guide that's used to get a very, then that's used as a kind of goal for each local node to do a local optimization. So going on to slide 23, this gives a little more detail about the methodology, which, that we don't have to go through those details now. And so basically the idea, if we go back to slide 24, is that what we're doing here is we're solving the optimal power flow problem, but in a decentralized way. So we're computing the required inverter control for each inverter to the network so that their local results, if viewed globally, would achieve something close to the optimal power flow. Okay, so let's go on to slide 25. There's a set of results. So we've worked on this again for these simulated networks, we've shown results for voltage control. So if we do no control, what the voltage is, if we apply the regression-based technique, what the voltage is. We can go on to slide 26. Again, this shows some of the results for that simulated network in terms of the voltage for both the regression-based method and without control. Okay, so let's go on to slide 27. This just gives a summary of the second part of my talk, which is this basically this decentralizing the optimal power flow with machine learning using this regression-based inverter control. What did we do? In summary, we decentralized the control, assuming that there's probably very little communication between the nodes. We automated, it has the potential, I would say, to automate otherwise extensive tuning. We optimized objectives, or it gives us a framework for optimizing objectives, such as, the allowable renewables in the network, minimize losses, voltage optimization. We can incorporate safety constraints through the optimization procedure, and also work with legacy equipment. So where are we going with this? We have a project now related to privacy of this. So in a decentralized optimization, when you share some variable, how do you share some variables with neighboring nodes? How do you do it in a way that preserves privacy? And we're interested in some of these other problems as well. I think privacy has been the big thing that we've been working on over the past few months. Okay, so this is a project that we worked on, again, with Roel Daube and a master's student who was visiting Oskar von Meier and others. And so that's kind of moving in, again, under the theme of model-based incorporating machine learning to do both estimation and control in the power grid. Okay, so let's go to slide 28 now, and I'm back to the outline. We're on the last piece of the talk, which is moving on to a current study we have, which is a demand response study in California. And as I said, this project is, it's a project that we started about 2 years ago, but the study's been going on for, about a year. And we're using data from a company that we're collaborating with. It's a San Francisco-based energy aggregator company that has as its customers individual households. And it is a company that is trying to participate in the California energy market by guaranteeing certain either supply or demand, by guaranteeing energy to be available or to use up energy in certain periods. And so it's doing this by incentivizing its customers, basically incentivizing its customers to lower their energy during certain peak periods by giving them points, which are translatable to saving money. So let me just go to the point of this, because I think this is something that we've been working on, which is, I think, quite relevant for our demand response study in the PCARI project. So let's move on to slide 29. And this just is just to say that demand response is, it's exactly what it sounds like. So changes in electric usage by end-use customers from their normal consumption patterns in response to changes in the price of electricity over time, or to incentive payments, and that's what this company that we're working with is doing, designed to induce lower energy use at times of high wholesale market prices or when system reliability is jeopardized. Okay, so the next slide, slide 30, it kind of describes the focus of what we've been doing. And it's a really interesting problem. It's not just that of understanding, well, okay, the heart of the problem here is to try to understand an individual customer's use behavior and how to incentivize individual customers to reduce energy at specific times. And so our role in this project has been to, from data available of both, how customers, individual customers, their usage patterns, but also data available of how those customers, when they've received a message from the company telling them or incentivizing them to turn off an appliance, for example, or reduce energy by turning off an appliance, how they respond to that. So do they respond typically? Do they not respond? Do they respond at different times of the day? What is the best time or way to be able to get a customer to respond, or are they completely unresponsive? And so this is it's an interesting problem from a kind of machine learning point of view, because you're trying to estimate what a customer would, or what a consumer would do, yet you're doing it from data where you've only ever seen them either not respond or respond. So in some sense, you're doing what is called, you're estimating the counterfactual, what customers would have done had they received a message, or the counter is what would they have done had they not received a message. And so the problem becomes a very interesting problem that, machine learning is very good at prediction. It's not very good at estimating causation or causal effects. And so the heart of this, again, it sort of speaks to this theme of combining machine learning with modeling, is to try to use the data in a way that we can estimate individual treatment effects, estimate, what is the causal effect of sending a particular message to a customer. And so this chart here on slide 30 shows the kind of, the pieces of this problem that we work on, the pre-processing, the counterfactual estimation, and then the estimation of individual treatment effects. If we go to slide 31, I'm not going to go through this detail now, but basically we're using techniques from economics to estimate this individual treatment effect, and I think the really interesting thing here is that these techniques have been used a lot in randomized controlled trials in economics, but they haven't typically in the past been applied to these kinds of systems with significant physical dynamics, like the energy grid that we're working on. So that's been, I think it's for us, it's been quite an exciting project, which brings in a lot of data, a lot of machine learning, the physical sort of dynamics of the system, as well as kind of the human aspect. How do we, what individual consumers, how to incentivize them, and how do you design experiments to figure out what the best incentivization is. So, for example, this company is not only providing points for saving money on energy bills, but they're also incentivizing customers by providing free smart thermostats that customers can install. And then those are automated devices that the company can actually, have direct control over. You don't have to be at home to have an energy reduction, for example. It can be done automatically. Okay, so let's go on to slide 32. This just goes into a little bit more detail about how we estimate the counterfactual. So, basically, and this is often called this fundamental problem of causal inference. So you can observe either, if you're working with a living lab, you can observe sort of one trace going through the experiment, but you can't see what would have happened had you not applied that control experiment. And so you have to estimate that from the data, and that's kind of a new problem here. Okay, let's go on to slide 33. This shows some of our initial results here. This is the plot of the, on the y-axis are the users. These are the customers of the company. And what the plot is showing is the sort of the variability around the individual treatment effects. So the number of users that are going to respond positively or negative, or not at all, or in some cases negatively to an incentivization. And it's individuals that looks at each individual customer and figures out, the methodology should figure out which customers to, which customers are going to respond, for example, at this time of day with this particular incentivization scheme. Okay, let's go to the next slide, which is entitled, well, again, it's the individual treatment effect estimation. This just shows some of our initial results over the first. We did this about 5 months ago with a few months worth of data, and since then we've been getting more and more customers on board and collecting their data. So we're going to be doing a phase 2 of this to estimate, individual. You can see a map from California of where a lot of these customers are coming. Okay, so let's go now to this is the last slide. I call it a summary, and I'm really just sort of revisiting the 3 problems that we talked about. We motivated the problem by thinking about contracts, and that's really how we got into this project. But really, I would say our work so far and the kind of publications that we have so far are kind of going back a little bit to the basics, to the problem of distribution grid state estimation when you don't have a whole lot of measurements. You've got more measurements than you had before, but you still have to do a lot of estimation. We talked about fully decentralized policies for optimal power flow, so a nice control problem. And then we ended by talking about a current demand response study that we're focusing on, where I think the key hard problem here has been to estimate individual treatment effects for individual consumers. And so I'd like to finish by saying this kind of gives, I would say it's more of a backdrop for the work that we're, some of these are, of course, funded under our PCARI project, in particular project 1, the estimation, and 2, the optimal power flow problem. But where we see it right now is it's given us a backdrop to these problems that we're focusing on in PCARI of contracting frameworks for demand side management. So some of these components that are needed, going from the measurements that Sasha talked about this morning through to the kind of the analytics on those measurements and how we do estimation with those and how we think about doing control with those. With that, I'd like to conclude, and I really welcome any questions, and I'll be around in this afternoon to participate in the discussion as well. So thank you very much.
Thank you very much, Claire. Are there questions for Claire? I think she could take 1 or 2 questions, or we could save those questions for the open forum later on. Maybe, well, I have a question. Claire? Hello, Claire?
Can you hear me?
Yes.
I can hear you. Yeah. Please ask your question.
Yeah. What are the principles that we can borrow from all of this research that would contribute to the design of interruptible load contracts for our case here in the Philippines?
Yeah, so that is something that we've been thinking about. And I think that some of the basics, as I sort of said, going back to the basics. So we need to have this data pipeline for forecasting and state estimation, and that's really this first project that I talked about. The optimal power flow problem, I don't think that's completely relevant for thinking about contracts, the interruptible load program, for example. But I think that I think the thing to pull out of like that principle there is really the decentralized component. How to be able to take some global objective for the grid and to translate that into local objectives at individual loads, or in the case that we solved it with individual inverters. So I think there's a principle in this, a decentralized implementation of an optimization problem that gives us a design of a contract that gives us optimal results throughout the grid. So there's some very, I would say, some sort of, fundamental ideas in estimation and optimization, which translate to the problems of contracting frameworks that we're looking at in PCARI.
Okay, Claire, thank you. Maybe we could, for the next couple of speakers, Alan and Audie will be able to demonstrate those principles of decentralized solutions to solving global problems.